Okay, our next talk will be Artane Siad, and he's going to tell us about class groups of monogenic fields.
Yeah, so I'll tell you about class groups and monogenic fields at the very end. So for now, we're going to start with a simple example due to common answer, which I think is quite instructive. So, but first I'll start with a bit of philosophy. So, yeah. So objects should appear in nature with frequency inversely proportional to the size of their automorphism groups. So seems a bit random, but if you think about it for a second, it's less likely that it's more likely to get something which is rather disordered if you just look in nature. And so if something has a lot of symmetries, you should sort of see it, not as often for things that are really chaotic. We'll start to do some mathematics with this piece of philosophy, and you can ask the question of what is a random group? So if you have two finite groups, when should one appear sort of more often than the other? And if we can make something quantitative out of this, that'd be great. And so one way to generate random groups is just to sit down and start writing down multiplication tables in a finite set. Most of them are not going to give you a group structure, but some of them will. And you can ask to count them. So, so this example is using one Lenstra, and I think it's quite nice. So the setup is you start with a finite set with n elements E, and a group G with a multiplication of order n. Okay. And you ask how many multiplication tables can you write down on E that makes it into a group isomorphic to G. So if you're looking to have fun, you can start just writing stuff down, and you'll realize most of them don't give you a multiplication table for a group. You don't have an identity, associativity fails, everything can fail. But there's a way of sort of counting these things very naturally. And the point is, you just look at the multiplication table you have for the group. And if you replace you substitute each element of the group and give it a name in E with some bijection, this gives you a multiplication table. So that makes it to a group isomorphic to G. And so you have your bijection, and this is a way of just writing down that you give it a name and pull it back. Okay, and you can get all multiplication tables for E that make it isomorphic to G this way. Somehow, if you write down two of them, you might actually end up writing down the same thing. And so in order to count them, you just notice that sort of the symmetric group on G, or symmetric group on all the sort of elements of G, acts transitively on the set of valid multiplication tables. And in fact, it acts in the following way. You just sort of do this. And you'll notice that if you look for things that stabilize your multiplication table, it's precisely sort of F's that are actually, so bijections from G to G that are actually homomorphisms. Those are the automorphisms. And so you have a transitive action of SG in the set of valid multiplication tables whose stabilizer is automorphism of G. And so the answer to the question is that you have n factorial over number of automorphisms of G. And so sort of, if you start writing down groups at random, you'll see a group more often than another one, or order n, exactly with proportions sort of inversely, with ratios sort of inversely proportional to the size of the automorphism groups. So somehow this piece of philosophy, if you do the stupidest thing you can, sort of shows up. So you can hope that this is sort of true in general for a lot of structures that sort of algebraic structures that occur in nature randomly. And so if you want to generalize this example, the natural frameworks to sort of work with sort of group and measures, and so I'll just say a few words about this. So in other words, you want to start with a sort of some category or some set of algebraic objects, consider them up to isomorphism, and just remember that you have automorphisms. So you start with a category, you ask for it to be skeletal and groupoid, so you just ask to remember automorphisms and isomorphism classes. And then you can put sort of probability measures on these things in certain nice scenarios, and you just want to do what we just did. You just want to define the probability that you land on a particular isomorphism class as being inversely proportional to the size of the automorphism. And in other words, you want to make definitions like the following in order to get a probability measure. Do exactly this, and you sort of divide like this in order to get a probability measure, right? You want the mass to be one, the entire system. So you can't always do this. For example, you'd like this thing to sort of converge so you can actually normalize things. And sometimes the structures you have infinite sort of automorphism groups, and then it introduces a bit more complexity. You can get around these things, around the second thing, but the first thing is quite hard to get around. So, so these things are grouped measures, and the thing that shows up on the bottom is something quite natural, and it's called the groupoid cardinality. So this is the denominator of the this thing. And so, okay, so we made a definition, and now let's see if we get some things that are interesting from it. So if you look at the category of finite sets, the probability that you get a set of length n using this definition is 1 over e divided times 1 over n factorial. So if you remember your probability, this looks like a Poisson distribution with mean 1. So I don't know your opinion on Poisson distributions, but they seem to be pretty natural, and so seems to be a pretty good definition. And yeah, another thing you can do is look at finite abelian P groups, and you ask for the probability that you get a particular abelian group A. That's going to be something. It's going to, you can write down what the answer should be in terms of what we had on the board before. What's sort of more instructive is this following interpretation for it, which is that you can actually get this probability as the limit of some sort of process. And this process is you take random n by n matrices with entries in the p-adic numbers, and you look at their co-kernels, and you count sort of number that are isomorphic to A, or the probability here, and you let the limit of the size of the matrices go to infinity, and you'll get exactly the groupoid measure you want.
What do you mean by random matrix?
Yeah, so IID the entries, and the entries are in ZP, and you have some R measure for each entry. That seems also pretty natural. It's a way of kind of like just writing generators and relations for a finite abelian P group. And if you do this in this sort of obvious way, you'll actually get this natural thing. And now, okay, so done with the philosophy, now with the number theory. So let's see where these kinds of things show up in number theory. So the thing I'm interested in are class groups. And so you start with a number field, and you look at algebraic integers in the number field. That gives you the ring of integers of the number field, okay? And then you have a very important variant for number fields, which is the class group. And this is just the quotient of the fractional ideals of OK by the principal of fractional ideals. Okay, so you don't do number theory, maybe it doesn't mean much to you, but here's an interpretation. It's a finite abelian group, so that's good. And it measures how far the ring of integers is from being a UFD. So so for number fields, the property of uniquely factoring into reducible sort of failed, you know, and this measures how much it fails. And so as an instructive example, there's a theorem of Carlis that explains what class number 2 means. So if you have a field and it's sort of class group as order 2, so it's not 2, then it's true if and only if every algebraic integer in your number field, when you take its decomposition into a product of irreducibles, that decomposition has the exact same length for any decomposition. Somehow it's if you have the smallest class number you want, you lose uniqueness, but you keep uniqueness of length in terms of factorization.
So I guess class number 1 are 2. For class number 1, it's clearly true.
Yes.
So
I apologize to Carlos. Yes. So a class number less than or equal to 2. Okay. And so sort of Gauss was one of the first ones to sort of ask questions about class numbers for number fields, and he asked sort of statistical sort of flavored questions. So
Actually, to be exact, he asked it not for number field, but for orders, and it was answered by the Rickley. That there are orders in from binary quadratic forms implemented in class number 1.
right.
He certainly didn't ask for square tree.
Okay.
But I agree that's the problem.
Okay, so yeah, so I'm just going to talk about number of fields. The rest of my slide is wrong with this. Okay. So yes, are there infinitely many? And you can ask more ambitious questions, which is which class groups of here is the class group of a number field? So also for sort of orders or Dedekind domains, I think this is already answered, but and with what frequency? And the answer is that you'll know that every finite abelian group shows up for a number field, and you don't know that a single one shows up infinitely often. So these things are quite mysterious still. And sort of the thing that happened when we got computers that we were able to compute a bunch of these, and when I say we, I mean humans. And here's the thing we notice: we get things that are quite random. So if you fix it,
Gauss was computing himself, and he made it on basis of the data.
So you fix a degree and a signature, and a prime p which doesn't divide m. And you look at the sort of p primary part of the class group as a random variable that goes from number fields of that particular degree and signature into p groups. And from what I've told you, you can put a natural sort of measure on finite abelian p groups. And the dream is that the distribution of this random variable here matches a natural distribution of finite abelian p groups. And how you sort of test these things is that if you put some kind of function here, you have some sort of density measure. It's really a measure, but it's a density. And so you can integrate functions against it and you can sort of push it forward and test these things. And so it turns out that's not quite true, except for imaginary quadratic fields. So the measure I wrote down for finite abelian p groups doesn't actually work. And you need to go to sort of things that are a bit more structured. In essence, you need to sort of keep track of sort of the influence of units, or sort of the group of units. And so when you do that, you get the general case of these conjectures of Cohen-Lunsford, Artane, and Mal. And sort of the point is you have some sort of measure or sort of density coming from putting a height function on this. So you look at all fields of a certain up to a bounded height, and then you just put the uniform measure, probability measure on there, and you can integrate functions. So I guess it gives you a notion of sort of integration, and you can push it forward. And then you can just compare what you get here to something on finite abelian p groups. And the problem is if you find some sort of discrepancy between the sort of obvious group or measure, but here, it sort of suggests the existence of a thing on top here, which is more structured, automorphism groups that are a bit different from there, that pushes down some natural groupoid measure that actually matches. And this is actually what happens in Cohen-Lunsford, Artane, and Mal. But these things here, you can actually sample with a computer. And so on interesting families in F, if you find some sort of discrepancy with whatever they have, it means you probably have some extra structure lying above. And so, so this is a theorem. So for the case for the case of cubics, which was obtained by Bhargava, Hankey, and Shankar, and for n bigger than 3, which was did by me, if you look at the first moment of two torsion in the class group for monogenic fields of degree n, it doesn't actually agree with the one predicted, the value predicted by Cohen-Lunsford, Artane, and Mal. And for me, it's conditional on a tail estimate for n bigger than or equal to 3.
What does monogenic mean? What does monogenic?
Oh, it means the ring of integers generated by one element of this algebra. So it's a very thin set, if you want, in the set of all things, but somehow it suggests the existence of an extra structure in the class group for this thing. Yeah, I'm looking to sort of find out that actually.
Tail estimates is the usual that you have a lower bound but not an upper bound.
I have an upper bound, not a lower bound, yeah.
Sorry.
Yeah.
It's a sub. You just sub up to 5.
Yeah, exactly. Yeah, and so yeah, I guess the point is that you can test some stuff with a computer, and if you find that it doesn't agree somehow, it means there's probably something interesting. And so it's a kind of a framework for finding interesting things, just compute stuff. Maybe there's something there or not. Okay, so I think that's time, and thank you.
So when you say it doesn't agree, means the number's not the number predicted. That's it. That's all you know.
Yeah, but somehow, that's right. But somehow, Melanie Wood has all these theorems that say somehow if you look at moments, these in a lot of cases determine the
Do you have the
distribution.
G up there?
Sorry?
Does she know what that extra structure is?
No, I'm just saying like Quinn-Lunsford type sort of distributions sort of are determined by their moments. And so if you find a moment that's different.
And I understand that. I'm asking, is that what you found? Just one moment, that the moment is not what it should be, but
Yes, yeah, that-
further explanation.
Well, we're working on it, so.
Let's thank Artane. Any more questions?
In the case of cubic fields, you have this.
Mondragon and Arul have it in the case of cubics, but I have it for n bigger, like all degrees bigger than cubics.
And any signature? Any signature?
Any signature, yeah. So I mean, for even degree, there weren't really heuristics, but there are now for these things. You have to take out genus theory to sort of see these things, but when you do, yeah, it's still different.
But for monogenic fields.
Yeah.
How do you list monogenic field?
Okay, so yeah, you just work with the polynomials and you put maximality conditions.
And the case of monogenic field should be different from monogenic orders.
Not so much. You still see an increase from monogenic orders, yeah.
Okay, let's thank Artane again.